In this example problem, we have a race car that's traveling in a straight line and going to assume uniform acceleration starting from rest, achieving 250 miles per hour at the end of 0.125 miles. That's an eighth of a mile. And your task is to determine the average acceleration. Because we do have the assumption of constant acceleration, average acceleration, we can use the kinematic equations. We do not know the time, so we'll have to pick an equation that will be useful that does not have time as a variable. But first, I would suggest you make a little sketch of the problem. So some sort of race car, 0 miles per hour, at the end of 0.125 miles, 260 miles per hour. So what about that equation? Well, we have a final velocity, we have an initial velocity, we have a distance. We want to determine the acceleration. Our kinematic equation should not have time as a variable because that would be two unknowns, acceleration and time. So the one that satisfies the need here for this problem would be final velocity squared equals the initial velocity squared plus 2 times the acceleration value times the distance traveled. And we would like to work this in the metric system. So these numbers come from common measurements in the United States, but I want to be in the metric system. So 250 miles per hour. There is a conversion factor, 0.447 meters per second is equivalent to 1 mile per hour. The mile per hour units will cancel, and we end up with 111.8 roughly meters per second. When you're converting from miles per hour to meters per second, your meters per second number should be smaller, should be about half as large as the mile per hour number. Then the distance also needs to be converted to metric. 0.125 miles, 1609 meters for 1 mile. The miles units cancel, and we end up 201.1 meters roughly. I've rounded a little bit. So putting those numbers into our equation, 111.8 meters per second, don't forget to square that final velocity, equals initial velocity squared plus 2 times a times 201.1. So we need to solve for a. So I need to ignore the 0 squared. I need to divide both sides by 2, divide both sides by 201.1. And we come to this point. Let's look at the units just a little bit. When we square this 111.8 number, I'll have meters squared over seconds squared. I have meters in the denominator. One factor of meters will cancel, and we'll be left with units meters per second squared, as we should for acceleration. You should pause the video, use your calculator, come back in 20 seconds. Welcome back. So the acceleration number you found hopefully is near 31.1 meters per second squared. Is that a reasonable number? Well, what can we compare it to? Let's convert the units again. Instead of meters per second squared, let's convert it to Gs. 1 G is 9.8 meters per second squared on the surface of the Earth. So 31.1 divided by 9.8, I get about 3.2 Gs. And I did a little bit of looking up. This is roughly the acceleration when astronauts or cosmonauts leave the Earth to go into orbit around the Earth, in order of 3 to 4 Gs. A trained military pilot can withstand 9 Gs. So this number is not unreasonable, 3.2 Gs. But we came up with this number after making a sketch and thinking about what equation we were going to select. We select an equation that does not have time, and then we convert to a standard set of units. The metric is preferred choice. And we solve for the acceleration. We do a little thinking if we get a reasonable result. And I hope that you'll continue practicing with the equations. Ask your instructor if you have questions. And you can also view some other mini lectures and sample problems. You can see an annotated list of my YouTube videos, physics.gpclements.com and astronomy.gpclements.com, a little bit more wide-ranging, a sky calendar for what's happening through the months of the year in the sky, and astronomy mini lectures and some sample problems for astronomy. So hope you keep practicing and continue your studies.